Hello, my name is Jeremy Seek. I'm a professor here at Indiana University, and this video is about learning the Deduce proof assistant. So in a previous video, we introduced the basics of programming in Deduce, and today we're going to take our first steps in writing proofs using the Deduce language. Okay. So what we've got up on the screen here already are some of the things that we created last time in that first video about programming in Deduce. We've got a union defined here that defines essentially a linked list of integers. And we've got a recursive function that computes the length of that list. And then we've also got, and that's using this particular list data type. And we've also got an example down here of this search function that that instead of working on this uint list, it's now using the generic list from the standard library of Deduce. Okay, so we're importing with this import list. So we're going to be using some of these things as we talk about doing proofs in Deduce. Okay, so with that, we'll move on and learn about writing theorems. So to create a theorem, you start off just by saying, okay, here we have the keyword theorem, and then we need to give a label to the theorem. Here, we're just going to have a kind of a goofy label called prove true. And in fact, the very first theorem we're going to prove is completely trivial. It's just the formula true. Unfortunately, this might be so simple that it's confusing. You would never write this as a theorem because it's so trivial. But you might be proving some complicated theorem, and as you're going through the proof, your current goal, the thing that you have to prove, could get simpler and simpler, and it might at some point just be the formula true. Okay, and then you have to know how to deal with that. And the proof for the formula true in Deduce is very simple. It's just a period. Okay, so if you get to a place in your proof where you have the goal of what you need to prove is true, you can just type in a period. So here we go. Let's see if this proof is valid. This is the simplest possible proof in Deduce. And then down here you can see that Deduce has declared that this file is valid. So indeed, this theorem and this proof are all good. Okay, so this was all about, okay, what if the formula you're trying to prove is literally just the formula true? You prove that with a period. Okay, so that was super simple. Let's start moving on to something a little bit more interesting. So suppose we have we call the function len on an empty list. Right. All right. So if we call length on the empty list, that should give us back 0, right? So it should be true that 0 is equal to length of empty. Okay. And so, how can we convince Deduce? How can we write a proof that attests to that fact? Okay. Oh, and by the way, when you get to the end of a proof, then you can go ahead and type in the end keyword here. Okay, so actually what I'm going to do here is show you what it looks like to write an incomplete proof. So I put a question mark there saying, hey, I just haven't finished this proof yet. And when you put a question mark there, instead of an actual proof, then you get a message like the one down below that says, hey, you've got an incomplete proof. The current goal that needs to be proved to complete the proof is this formula here, 0 equals length of empty, right? Okay, which is, in this case, is just a repeat of that formula. Okay. All right, so what do we do here in Deduce? Well, you might already wonder, like, well, why doesn't Deduce just say, yes, this is valid, right? Like, why do I have to do anything? And it turns out that when Deduce sees a function call like length on empty, Deduce will only sort of expand that function when you tell it to. Okay, so there's various reasons for this. The main reason is that you actually could have, because of recursive functions, you could have sort of a cascade of function calls happen if it was all automatic. And then it can actually be quite confusing as to what's going on. You think you're proving one thing and all of a sudden it changes to something else out from under you. Okay, so instead you have to tell Deduce sort of one step at a time to sort of expand function calls. So here we want to tell it to do sort of expand the function call of length on empty. In fact, you can see that that's you can see that Deduce is giving us some advice. It's actually telling us that expand is one of the things we want to do. Okay, so what we can do is we can say expand len, and we can put that right above the question mark there, and we can try this again. And now, all of a sudden, the goal has changed. And it changed quite a bit. Now it's just saying true. Okay, so let's stop for a moment and see what happened. Okay, so kind of step by step here. So what happened was, our old goal was 0 equals length of empty, right? But then Deduce took the definition of length from up here, says length of empty is equal to 0, and it sort of replaced this expression here with 0. Okay, so that's what expand does. So at that point, you've got 0 equals 0. Okay, now Deduce does do a little bit of things automatically. So whenever Deduce sees an equality with like literally the same syntactic thing on both sides, then Deduce will just reduce that down to true, which is what we see down here. Okay. So at that point, we can, as we learned a minute ago, we can just use period, and that completes the proof. Okay? So with this little example, we've seen how to use expand. Okay? And that's how to expand the definition of a function as it's applied to an argument. Okay, let's see a little bit more complicated example of expand. Okay, so let's say we do search. We apply our search function up here to a list that contains like 4, 3, and 8. And maybe we're searching for 8. Okay, and that should give us the index 0, 1, 2. Okay, so index 2, so that should be a true statement. So we should be able to write a proof of that. Okay, so there's our goal. We need to prove that. So let's go ahead and expand search. What we're going to see is that, okay, so this square bracket notation, if you remember from last time, is actually shorthand for node of node of node of node, right? And up here, we can see that there's a definition, search. If you have search applied to a node, then it's going to do this conditional if, thing, and then expand to 1 plus blah, okay? And the very first call to search here, it's going to be comparing 4. 4 will be our x, and 2 will be our y. Or no, I'm sorry, and 8 will be our y. 4 and 8 are different, so we're going to end up going to this else branch. So we're expecting to see, this call to search down here and the goal turning into 1 plus search, but with a shorter list. Okay, so let's go ahead and see if I was right about that. Okay, boom. Down here, we've expanded one call to search, and now we're looking at the recursive call on the rest of the list, 3, 8. Okay. Now we can do expand again, right? And it's going to sort of dive even further into the list, right? So now it's saying 2 plus search of looking for 8 in the list 8. By the way, notice that if we were just reading off of the definition of search, 1 plus, we would see 1 plus 1 plus search, blah, blah, blah. But Deduce does some of arithmetic simplification for us automatically. It turned the 1 plus 1 into 2, as you'd expect. Okay, great. So let's do one more expansion of search. And boom, now we're done. And we can just conclude with a period. Okay. Now, one thing to notice here with this proof that we've just finished is it doesn't talk about what our goals were or how the goals changed as we were going along in the proof. And that might actually make the proof a little bit hard to read. Okay. So sometimes what I like to do is I like to sort of, in some sense, better document my proof. Okay. So the way I'll do that, actually, let's comment out the rest of the proof for now and rewind to this spot here. And what I like to do is I'll take the goal and I'm just going to copy and paste it in here using the show keyword. Okay, so the show keyword is just a way of saying, here's the current goal. Please double check that I've typed it in right, that this is indeed the current goal. But other than that, it doesn't change anything, right? So you can just sprinkle those in whenever you want. Okay, now we're going to do one more expand of search, and our goal changes again. And if I want to, I can insert another show, just to kind of keep track of what was happening. And then, again, this final one is just true. So there we go. So now this proof is a little bit, easier to understand what was going on. As you can see that we were sort of like, we started off doing a search on the whole list, and then it's recursively unfolding, and now we only, we've got 1 plus search on the rest of the list, and another step there. So you can see what's happening better. Okay, so it's really just a matter of taste in terms of what you want your proofs to look like, in terms of how often you use show to sort of document what's going on. Okay, so that's all I wanted to say for the moment about expand and show. So the next thing I want to talk about is a for all formula. Okay. And so here's an example theorem that would include a for all. Okay, and so the way you say for all in Deduce is just the word all. So you say all, and then you introduce a variable. This variable is like a placeholder. That's this x here is a placeholder for sort of all the unsigned integers. Okay, so it's like a representative for all of them in some sense, or one of them. Okay, and so here I'm going to type in a formula that's going to be true, sort of for every integer, right? And the reason it's going to be true for every integer is that this formula actually doesn't care what the integer is, right? So here we're saying the length of a node, right, of a linked list, where the rest is empty, well, the length of that should be 1, right? Length of the empty is 0. Then we add one more node. We should have length 1. Okay, and it doesn't matter what the integer is. Okay, so we should be able to say this is true for all x, where x is an integer. Okay. All right. So now we need to do a proof of this. So let's see what Deduce gives us as advice. Okay. All right, so down here, it says we've got this incomplete proof. Our goal has a for all form. It's an all formula, right? So advice is saying prove this all formula with arbitrary. Okay. So this arbitrary, this is the standard way in mathematics that you prove a for all. It might sound a little bit different. In a textbook, you might say, let x be an arbitrary integer or something like that. And so here we're just being a little bit more terse. We just say arbitrary x. Okay. So now x is this integer that we don't know anything about other than it's an integer. We don't know whether it's 0 or 1 or 2 or whatever. But hopefully we can actually still do this proof without knowing what it is. Okay, and so what we need to prove here, is that the length of node blah is equal to 1. Okay, well, kind of like what we did last time, we should be thinking, oh, maybe we can expand the definition of length here. Okay, right, length of node equals 1 plus, the rest. Okay, so we can do expand len, and that should change our... Actually, before we do that, I want to show you what happens just from the arbitrary. Okay, so we put that arbitrary in, and now look at our goal. The goal used to say all x blah, blah, blah. Now the all x is gone, right? The arbitrary got rid of that, and now we just need to prove this statement, okay? So that's where now we can do expand len. All right, so expanded length once, and now it's referring to length of empty, right? So let's do expand length again. And now we're down to true. So indeed, we were able to prove this for all statement, okay, using an arbitrary as our proof method, okay. By the way, oftentimes when we do expands, we sometimes want to expand a couple different functions or even the same function. So you can say expand and use vertical bars in between different names. So you can do it like that. And also if it's the same function a couple times, you can say sort of 2 times to tell it how many times you want to expand length. Okay, let's look at an example use of this theorem. So suppose we want to prove that the length of node 42 empty. So now this is, an actual linked list with 42 in it, just one element. Let's say we want to prove that the length of that particular list is equal to 1. Okay. I mean, we could do this directly, of course, by expanding the definition of len. But let's, here I want to demonstrate how you can use a for all to prove something else. Okay. So what we're going to do here is, so this for all statement, I can refer to the len1 theorem. Okay, that's the name of this theorem, and it's all, so I can plug in a particular choice for x by using these square brackets and then plugging in a particular entity, right? It has to be whatever kind of entity matches the type of the variable here. So 42 is indeed an unsigned integer. So indeed that's what I'll get there. In fact, let's see if I just try to provide that as the proof. Okay, this isn't going to work, but right. So it's saying the proof formula is this, right? So when I instantiated len1 of 42, that got rid of the all and it gave me back this formula. But now you can see that the x has been replaced by 42. But that does not match the goal, right? The goal has it just flipped around. So there's actually a couple ways I could fix this. One way is you can use the symmetric keyword to flip a formula around, and boom, or I should say flip an equality around. Okay, and so that proved that statement. Another option. Let's just do this again. Is I can once you have len1 of 42, let's get rid of this, right? Once I refer to this formula, I now have an equation. And so in Deduce, you can use an equation to sort of simplify a formula. So here we have our goal, and what I could do is I could use this equation up here to simplify the right-hand side down to 1. And once we have 1 equals 1, then it's going to be trivial. So the way you say use an equation to simplify the current goal is you say replace, and then you give it the equation. In this case, it's len 142. Okay. Right. So len 1. I'm just maybe make a comment here that actually, yeah. Right. Len 142 is this equation. So when I say replace, it's gonna look for matches of the left-hand side here in our formula. It's going to find it here, and then it's going to replace it with the other side of the equation. Okay. So let's go ahead and do that. And it should now simplify to true, because of course, 1 equals 1 is going to be trivially true. Okay. Okay, so there's sort of 2 things we learned here. One is that you can instantiate a for all with the square brackets. So if you've got this formula that's an all and you want to use that proof somewhere else, you can plug in whatever you want in the square brackets. And the other thing we learned is to use replace. So if you have an equation and you want to sort of use that equation to simplify your goal, you can use the replace keyword. Okay, all right, we just have 2 more concepts to cover in this video. The next concept we want to cover is implication, or another way to say it is if you've got if in your formulas. Okay, so here we're going to be, this might, if you've ever studied first order logic or propositional logic, this is going to sort of maybe be a blast from the past. So we're going to have this fairly complex formula here. Right, we've got all these nested if-then formulas. Okay. So, right, what does this whole thing say? It says, well, if this formula is true, then this formula better be true. Okay. And then sort of diving into these formulas, it's sort of, we've got even more nested ifs, right? This one says like, oh, if P is true, then the rest of this better be true. And then this one says, well, if Q is true, then R has to be true as well, right? Okay, so let's try to prove this theorem. This is kind of a fun logic puzzle here. All right, so we start off right off the bat. Our goal is an all formula, right? This all is at the top there. And so Deduce is suggesting, giving us some advice that we use arbitrary to start off the proof. That's some good advice. Okay, now the all is gone. And now we've got a whole bunch of if-then formulas, right? And now the advice we're getting from Deduce is, and by the way, this is just sort of standard mathematical, this is how you prove an if-then formula in logic, okay? This is not special to Deduce. What is special to Deduce is just the syntax here of how you do it. So with Deduce, if you want to prove an if-then formula, you need to assume, write one of these assume statements, and the formula that you're going to assume, of course, is the premise, okay, which is this whole, the thing that came after the if but before the then. Okay, so we're going to go ahead and take that advice. The word label here, we get to pick whatever label we want. I'm going to just write premise there. Okay, and then I'm going to go ahead and paste the premise in there. And now we can move on. Right now our goal has simplified quite a bit. Right now our goal here, if Q, then blah, blah, blah. Right, that was the conclusion, right? So now we're trying to prove the conclusion of that old if-then, okay? Right, but of course our conclusion here is another if-then. So we need to assume Q here. I'm just going to use lowercase q to refer to the formula Q, right? Now our goal is simplified even further. Oh my goodness. Another if. Whoa. So we need another assume. This time it's P that we're assuming. All right, now we finally sort of get to the bottom of things. We're trying to prove R. We have a whole bunch of assumptions. Okay, so at this point, we got to start thinking about how to use our assumptions. Okay. And so maybe one thing we might be looking at here is, well, where on earth is there an R? Okay, well, oh, there's an R down here at the bottom of our premise. Okay, so that means the only way we're going to get through this is if we use this premise here. Okay, well, how do we use an if-then statement? Okay, well, you know, the answer is, I mean, this in logic, this is the rule modus ponens, okay, that's the Latin, but basically we need to provide a proof of P, and if we do that, then we will know that the rest of this is true. Okay, and indeed we have a proof of P right here, this assumption. Okay, so we can say, now what's interesting here is I'm going to show you a new sort of kind of statement in Deduce. And this is the kind of statement you use when you want to do forward reasoning. That is, you've got maybe some assumption or some fact that you've already proved, and you want to use that fact to prove some new thing, but the new thing you're proving is not your goal, right? Our goal is R, and we can't jump straight to R yet. Okay, what we're going to do is we're going to have, let's call it QR, right? We're going to prove the conclusion of this premise. Okay, so we can, here's the conclusion of our premise. I'm giving it a new label here. And now I need to say, so whenever I do one of these have statements, I need to give a proof for why this formula is true. And so the way I'm going to do that, so this is how you do modus ponens in Deduce. You say apply, and then you have your if-then, and then to, and then you need to provide a proof of your premise here. So P, okay, we have a proof of P right there. So we're gonna put P there. Let's see if Deduce is happy with that so far. Yep, Deduce is happy, and it's good all the way down to this spot where we're incomplete. Okay. Okay, well, we're still trying to get to R, but we're a little bit closer. Now we have this formula, and of course, we want to get to R here, so we need a proof of Q. Okay, well, look at right there. We already have our assumption Q. So now we can actually pretty much conclude the proof. We can say apply QR to Q. And we're going to be done at that point. Okay, so we just did modus ponens again to get all the way to R. So that's an example of using, you know, if you've got an if-then formula, both how do you prove an if-then formula? You do that using assume. And how do you use an if-then formula? That's where apply comes in. Okay. All right, so we got our if-then figured out. The last concept I want to go over is how to use sort of conjunction or just the word and. Okay. So this is an example of using and. Again, we're going to have a bunch of booleans, P, Q, and R. So now we're going to use and. So if P and Q and R, then R and P. Okay, so this is pretty obviously true. So we should be able to prove it. Of course, if we had a false statement, it would be impossible to prove. All right, so Deduce is giving us some advice about how to start out. We should be, we need to prove an all formula. We need to start out with by stating that P, Q, and R are arbitrary. Okay, now we have an if-then to prove. So we'll do the usual thing of assuming the premise. We'll just call it prem this time for short. Okay. All right, now we need to prove a conjunction. Okay, so this is this new thing I want to focus on here is how do you prove a statement about and. And right, the advice down here, it's saying, well, you have to prove each of its parts. So we need to prove R, we need to prove P, and then we can combine those proofs with a comma. Okay. All right, so actually here, let's do this. Let's do one of these halves where we're gonna prove R. But actually, instead of actually proving R, I'm just gonna say sorry and sort of cheat at the moment. Say, you know, I want to bypass that for now. I just want to pretend as if I've done those proofs. Okay. Right. Now, of course, we get some warning messages that I've left some proof unfinished. But now I have P and R as givens, as things that I've sort of already proved. And so now I can show you that to prove R and P, I'm just going to take little r, comma, little p, right? And Deduce is going to be happy about that. And now the only thing that's left to do is to fill in where the sorries are. Okay, so let's go ahead and work on that first sorry. Right, we need to, now we're in sort of this subproof. Okay, actually, you know what we can do here? We can, yeah. So we need to prove R. And so we need to look at our givens. Well, we have this premise that says P is true and Q is true and R is true. Okay. So yeah, that's, you know, the conjunction says that all the pieces are true, right? So in Deduce, you can just say, use the prem, and it's gonna know that, oh, you know, Deduce knows how conjunction works, and it's gonna be happy with that, right? So indeed, this bigger conjunction proved, you know, this single statement about R. Okay. All right, let's look at the next one here. We need to prove P. Well, again, P is in this conjunction labeled prem, so we can just put prem there. Okay, and boom, now we're done with this proof. All right, so again, what were we doing in this example here? Well, let's say you're trying to prove a formula that has an and in it. You can do that with a comma, and you have to prove each of its parts. So to prove R, you know, we had to go ahead and prove R, and we also had to prove P, right? There's our proof of P, and then we can put those two things together with the comma. Okay, so that's how you prove a conjunction. And then we also saw examples of how to use a conjunction, right? So to prove this if-then, we got to assume the premise, and the premise was a conjunction of P, Q, and R, right? And so we can just implicitly use, you know, that conjunction to prove any one of the parts. Okay, so that's the other thing to know about conjunction, is that when you want to use it, that can just implicitly, you can use this conjunction implicitly as any of its parts. Okay, so there's R there, and so Deduce was happy with that proof. Okay, so we've made it through to the end of this introduction. There's plenty more things to cover in terms of how to do proofs in Deduce, and we'll be covering those in later videos. I hope this was helpful, and talk to you later.